Hello everybody. Today we're finishing up our unit notes on Unit 1. So today I want to talk about applications. So trigonometry can be used to solve the missing angles and sides of a right triangle, as well as bearings between objects. We've actually done a few examples like this in the previous sections. Remember that when I say solve a triangle, it means to find all of the missing sides and all of the missing angles. So solving a triangle means finding anything that might be missing. I also want to talk about simple harmonic motion. Now, simple harmonic motion is the periodic or repetitive cycles nature of the trigonometric functions, and it's used for describing the motion of an object that oscillates or goes up and down, rotates or is moved by wave motion. For example, we can consider the weight that is bobbing up and down on the end of a spring, like this. Okay, or like this. Now, if the equilibrium is at the origin, then we use a sine function like this right here. And if the equilibrium is not at the origin, we can use a cosine function. So, the equations for simple harmonic motion are used right here. Amplitude is always the absolute value of A, just like it is in all of the other things that we've done. Period is 2 pi over B, the number of seconds per cycle, and frequency is B over 2 pi, or the number of cycles per second. So I know this is a lot of new things here, but what I really want to do is I want to do an example here. So suppose that a 10 centimeters is the maximum distance the weight moves vertically upward or down from its equilibrium at rest position. Now, because we know a couple things just from this first sentence. The equilibrium is at rest position, which means if it's at rest position, it means that it goes through the origin, which means we're using a sine function here. The other thing is we know that 10 centimeters is the maximum distance between the weight moving up vertically or down from this equilibrium or midline, as we've been calling it in other functions. So we know that 10 centimeters is the absolute value of A. So we can even say that A is equal to 10. Okay, so we figured out a whole bunch just from this first sentence. So suppose further that the time it takes for the weight to move from its maximum displacement above zero to its maximum displacement below zero and back again is 4 seconds. So what that means is a full cycle takes 4 seconds. So we now know that the period is equal to 4 seconds. Okay, so what we're going to do is we're going to do two things here. We're going to write the equation for the simple harmonic motion of the weight described in this scenario, and then we're going to find the frequency. So before we need to find anything, we have A, we need B here because we're not given B. Okay, because we're going to be using the formula D is equal to A sine of BT. Okay, so we have A, it's given right here in the function, but we don't have B. To find B, we do know the period. The period of the function is 2 pi over B, which was told to us is 4 seconds in the actual equation. So now all we have to do here is we need to solve for B. So what I'm going to do is I'm actually going to multiply both sides by B to get 2 pi is equal to 4B. And then I'm going to divide both sides by 4 to get B is equal to 2 pi divided by 4, or pi over 2. So we now know that B is equal to pi over 2. So now we can put everything together to find the equation for the simple harmonic motion of the weight described in the scenario. So we know that D is equal to A, or in this case 10 sine of B, which we just found was pi over 2 t. So here is the equation for this simple harmonic motion. So we have done what this first question was asking, so we can check it off. Second question was, what is the frequency of this harmonic motion? So we are told from above that frequency is equal to B over 2 pi. Now we know what B is because we just found it over here. So we know this is going to be pi over 2 divided by 2 pi. We're going to have to flip here. So we're going to keep the top, change the operation to multiplication, and flip the bottom. And if you look here, these pi's cancel out. So our frequency is equal to 1/4, or 1/4 cycle per second. And there's our frequency. So every 1 second, this will complete 1/4 of its cycle. So we found the equation and we found the frequency here. So we have answered the whole question. Okay, so let's do one last example here. Oh. Okay, example number 90, and it's our final example of the entire unit. So the following equation represents the movement of a pendulum in a grandfather clock. Okay, so D is equal to 6 cosine of 3 pi over 4 t. We're going to calculate the following things. The maximum displacement. Okay, remember the maximum displacement is also known as the amplitude here. So A is equal to 6, so we're going to take the absolute value of that, and our maximum displacement is 6. Okay, so frequency, as you guys may remember from the previous slide, we have frequency is equal to B over 2 pi. So we have B over 2 pi. Now, if we look at this equation, B is 3 pi over 4. So we have 3 pi over 4 divided by 2 pi. So we're going to keep change flip again. So we're going to keep the top, which is 3 pi over 4. We're going to change the operation to multiplication, and we're going to flip the bottom here. Now, there's not a lot of canceling other than these pi's. So now we're going to get 3 over 8 is our frequency. So 3/8 cycles per unit of time. In this case, they don't give us seconds or minutes, so we're just going to say per unit of time here. Per unit of time. Forgot the of here. I'll just rewrite it. Unit of time. There we go. Okay. So the last thing we're going to need to find is what is D when t is equal to 4. So all we have to do here is plug in 4 for t. So we're going to do 6 cosine of 3 pi over 4 times 4. Okay, so what we're going to do is we're actually going to cancel out these 4's, if it will let me. So we have 6 cosine of 3 pi. If you look in your unit circle, cosine of 3 pi is the same thing as if we find cosine of pi, and x at pi is -1. So we have 6 times -1. So D is equal to -6 when t is equal to 4. Okay, so these are just a couple examples of how we can use some applications to find simple harmonic motion. Okay, you might be asked to find a couple other applications like solving a triangle, as we talked about earlier. And so this actually concludes this section, the notes of the section, and the whole entire unit. So as always, if you guys have questions or concerns, please don't hesitate to join me in the Google Meet or give me an email. If you don't have any questions, I hope you have a fantastic day.